introduce you, Tom. So it's my great pleasure to welcome Thomas today, Thomas Peyrin, who is a professor in Singapore and a colleague I know since a long time. Thomas is famous for many contributions in symmetric crypto, in particular in lightweight crypto, where he's one of the probably most influential designer of many schemes, including some which are ISO standards and others which are in the final list of the CASA of the NIST competition for lightweight authenticated encryption schemes. And yeah, I'm happy to hear his talk on lightweight crypto and with a special focus on tweakable block-ciphers. Thomas, the floor is yours.
Thanks a lot for your introduction. So hello, everyone. Actually, sorry to say I made a little change on the outline because lightweight cryptography was quite a large topic to cover. So in the end, I decided to not put too much focus on tweakable block cipher, but just to give an overview of what were, I think, the most meaningful advances in the field of lightweight crypto. So some kind of summary of what happened in the past 15 years. So this was quite a hot topic, and this was already covering quite a long talk, so I will focus on that only. But if you're interested in more on the tweakable block cipher part of it, actually I will advise you to take a look at the invited talk I gave at FSC 2020, where I talk more about the tweakable block ciphers. So, oh, it's not working, my slides. Yes, okay. So I divided this presentation in 3 parts. First, I will try to explain a bit what is lightweight crypto, so what we call lightweight crypto, and why I believe it's a complex problem. It's mainly because it has many dimensions, and as soon as you touch one dimension, it changes another one, and it's hard for you to try to optimize everything at the same time. Second part, we will try to see how we actually design Cipher today and how we can make them lightweight. So what are the changes that we do to make them lightweight? And in the last part, I will try to cover what's the present and future of lightweight crypto, and basically trying to take a look at the competitions that have been organized and covering lightweight cryptography, and in particular, the NIST lightweight competition that is currently going. So I don't know what the audience knows about crypto already, so I would go very, very quickly on the basic of cryptography. I guess all of you already know about this. Sorry if this part is boring. But just to say that, of course, cryptography is divided into 2 parts: symmetric cryptography, where we assume that Alice and Bobs are two entities that already share some secret key. And for asymmetric cryptography, instead, you have a public key and a private key for each of the users. And the take-home message here is just that usually symmetric crypto is fast and small. Okay, the algorithm that we're using are very, very, very fast. And for asymmetric crypto, it's much, much more slower and larger. And you actually have one order, or sometimes several order of magnitudes compared to a symmetric crypto. So usually what happens for most security protocols, you use asymmetric cryptography to negotiate new keys and all the parameters of the protocol, and then you use symmetric key to actually do the encryption for long messages, etc. So when we're going to talk about lightweight crypto, we're going to talk about symmetric key lightweight crypto because it's already difficult for symmetric key. So if you want to do that for asymmetric, it's going to be even more difficult. Now I zoom inside symmetric key, and I think the way to see symmetric key crypto, the old way I would say to see symmetric key crypto is you have 2 groups: block ciphers and stream ciphers. So block ciphers first is basically a family of permutation that is parameterized by a secret key, your secret key K, that is shared between the 2 entities. And a block cipher ciphers blocks, like the name says. So it means that, for example, you have a plain text of size 128 bits. That's the most common size, the one that you have for AES, the current standard of block ciphers. And you're going to be encrypting these 128 bits and getting the ciphertext. Now, if you want to encrypt something else than 128 bits, then you need an operating mode on top of this. So this operating mode would tell you how you can use this cipher, this block cipher, to cipher smaller message than 128 bits, larger ones, maybe some that are not a multiple of 128 bits, etc. The other big groups are stream ciphers. Here, the idea is a little bit different. You have a pseudo-random number generator that is initialized, or actually not with S, but with the key and some initial value. So the secret key and some initial value. And this pseudo-random number generator will output some bits, which will be unknown from the attacker. And you directly use these bits bytes or digits, whatever digits you want to work with. And you directly use this output to cipher to add this to your plain text to get the cipher text. So the idea is a little bit different. Many people actually put hash functions in the group of symmetric cryptography. Actually, hash function have no key, so it does not really belong to symmetric cryptography. It has no key at all. But since most hash function that we are using today, they use the exactly same design principle as block ciphers, mostly, or stream ciphers a little bit, people usually put hash function in that group. So when we're going to talk about lightweight cryptography, we're going to talk about these type of primitives, but also hash function, actually. So that was I think the old way of seeing things. Now, personally, I view the division in different ways. I think people recently try to generalize a bit block ciphers and stream ciphers. And now we have two new groups. I will call this tweakable block ciphers. So tweakable block cipher is exactly the same thing as a block cipher. The only difference is that you have an extra input here to parameterize your permutation. And this extra input is called the tweak. And this value can be actually public. It looks like it's a small change and nothing much will change, like in terms of what you can do. But in fact, when you use that extra input in operating modes, it changes a lot because this tweak, you will be able to put some kind of counter, some domain separation, and this will make sure that in your chain of encryption that you're going to have in your operating mode, all the instances of your cipher will be different. And this, in terms of security proof, will change a lot. You will be able to get better, higher security, to get easier proofs, etc. So this is generalization, I would say, of block ciphers. And we can see the recent emerging of sponge functions. So this is a new framework, which is extremely popular right now in symmetric cryptography. It was proposed in 2007. So we can see actually sponge framework as a generalization of stream ciphers. Now, instead of having just a pseudo-random generator that output bits from the key and some IV, now you have this sponge function. So it's a permutation that can absorb some data. So you can give it some data, it will absorb it into this secret state. And you can ask it to extract some unknown bits from it. So you can get a few bits out of the state and use this bit for authentication purposes, for maybe encryption purposes, etc. And personally, I view this as a generalization of stream ciphers. So, okay, now this was just to give a very, very rough picture of where we are in symmetric cryptography. So first, what is now lightweight cryptography? So maybe you have already seen that, but all the devices that we're using today, they're getting cheaper and they're getting smaller and smaller. And actually now you even have devices that are completely embedded in our everyday lives. For example, Rfid tags. Okay, when you purchase maybe a T-shirt in some of your favorite shop, you might have a small tag that is attached to it, so you can directly make the payment automatically in some of your cashier. That's one example. But you have many applications of all these embedded devices for vehicle access control, smart cards, many applications for medical sensors. For example, if you have some sensor for your heart space, for example, wireless sensor in general, not just for medical purposes, home automation, etc. So you have really more and more devices everywhere, and on top of that, all these devices might be connected to the internet. And that's kind of one of the goals of these devices, is to potentially share some data, and so that this data can be exploited, or maybe also it will change the behavior of the device. So all these devices will form what we call now the Internet of Things, IoT. This is a very popular word at the moment, and it's estimated that it's going to grow a lot. Probably around 50 billion of IoT devices by 2030, by the latest estimations. Now, the problem is, of course, having these devices is great. Having all these new functionalities is great. But if you start connecting these devices to the internet, well, the internet is an insecure place, and you might have a lot of security problem. And on top of that, this is even more a problem than what the device that we are using now, because these devices in particular will be placed in unsecure environment, physically insecure environments. When you think about sensors, for example, wireless sensors, these will be devices that you throw in the wild, maybe to create some new network in places where you cannot. It's not easy to create a new network, and you can imagine that attacker actually having physical access to your device. So it means that the attacker here has even more power than in the classical model where you think of your PC, for example. Nobody will touch your PC. You have control of your PC, and nobody can access it. And so the problem also is that they are manipulating data that can be sensitive. So this depends on which application you're considering. But for example, if you are a company having a lot of stocks and of T-shirts, for example, and you have an RFID tag on all your shirts, you don't want another company to be able to scan and see what are your current stocks, to see if you're selling a lot of T-shirts or no. Well, for any application you can imagine, all the data that is used, transmitted, is going to be sensitive, at least for some people. So how do we protect it? Well, we already know how to do that. So this kind of problem is not new. We use cryptography. No problem with that, but the problem is that current cryptography standards that we are using is actually very complicated, because these devices are potentially so constrained in terms of many different parameters. One of the most obvious one is memory, for example. So it's going to be so constrained that you cannot apply the standard solutions. One way that the industry dealt with it is by using their own ciphers. They try to come up with some very, very lightweight cipher in some way. And unfortunately, as it is very often the case, as soon as some non-cryptographers try to come up with their own solution, trying to get the algorithm secrets that hope that nobody will manage to reverse engineering it, it will be fine. In general, this leads to disaster, and that was the case, for example, for keylock. This was used for opening your cars without key, or MyFare that was used then for example as a smart card for metro, for example in London, I think. So yeah, we cannot let the industry maybe without capabilities in cryptography to have their own solutions. So this was one topic that came as a research in the crypto community, is how to come up with lightweight algorithms. So I want first to give you some actual numbers so that we actually have an idea of what we're talking about. And let's take a look at RFID tags, for example. So RFID tags is just some small circuit, basically, with some very small circuit with some antenna attached to it. And you can have some reader. Some person can come up with a reader. And this reader will try to query all the RFID tags that are around, and all the RFID tag will reply or not, depending on your application, etc. So you have basically two types of RFID tags, the active one and the passive one. The active one means that basically it has a battery attached to it, so it has its own energy. It can act as a beacon, basically. And you also have a passive one, and the passive one have no battery at all. How are they powered is actually from the electromagnetic waves from the reader. So you have to be quite close range to make it work. So that's one basic separation for RFID tags. Now let's look at the numbers. We need actually authentication and confidentiality for some of the data that are in RFID tags. Most of the security protocols will be using block ciphers as a basic primitive, or sometimes hash function as well. So maybe we can take a look at the numbers and see if current standards can fit in an RFID tag. So you have different categories of RFID tag. The very cheap one that are very small, and you also have like larger ones. And of course, here what we are trying to deal with are the cheapest ones. So the cheapest one will be something around 1,000 to 15,000 logical gates, roughly. But this is for the entire RFID tag. And if you want to put security in that product, you cannot take the full space. You need to leave space for whatever application the company wants to make. So roughly, it's admitted that between 200 to 4,000 gates, logical gates, can be budgeted for security. Now, if you look at the standards, the current block cipher hash function that we have, roughly SHA-2, SHA-3, so that the hash function standard that we have right now, they will take about 10,000 gates to be implemented. And this actually is without the extra protocol you might need in order to use these hash functions to provide whatever security properties that you want. So this is actually a lower bound. If you take a look at AES, so the block cipher current standard, it's about 6,000 gates that you need to implement it. And again, this is without any mode, operating mode. So you will need a mode on top of this. So you will probably need much more than 6K gates. As I mentioned, if you look at asymmetric cryptography, it's even worse. Probably the lightest branch of asymmetric cryptography will be elliptic curve cryptography. And even if you want to make a point multiplication, this will require about 10 to 20 kilo gates to make this multiplication. And on top of this, it will require millions of cycles to make this multiplication. So not only it's going to be large, too large, but also it's going to be extremely slow. So actually, very recently, like 5 years ago, with some researchers, we published a new implementation of AES. So that's one way to make cryptography work, is to try to make better implementations, smaller implementations, so that it can fit, for example, Rfid tags. So what we did is to come up with a new implementation of AES. We managed to make it down to 1,600 logical gates. So it looks like now it's fitting, right? So one might be asking the question, is AES actually lightweight cipher? So is the problem solved? Well, yes, it's true that AES can be implemented in such a small number of gates, but actually, no, it's not solving the problem, because this small implementation has a data pass which is very, very small, actually 1 bit data pass. It means that every cycle you will handle just 1 bit. And of course, the number of operations, number of cycles you're going to have to do is going to be very huge. For this implementation, for example, we need around 1,000, 2,000 cycles. And this is bad first for the latency. It means you're going to have to wait a lot to get your output. Might not be very good for some application. But on top of that, energy consumption is linked directly to the number of cycles that you are using. Roughly, to get an estimation of how much energy you will be requiring, you can do area times the number of cycles, and this will give you some estimation, a very rough estimation, at least some kind of rankings, rough rankings between the different schemes. So this implementation actually is going to consume a lot of energy. So I give here in the table to give you some perspective. This is for AES, so different types of implementation, 1 bit at a time, so 1 bit data pass, 32-bit data pass, or round-based implementation, which means you use the entire state is updated in 1 clock cycles, and you're going to do the same number of cycles as the number of rounds there is in your ciphers. Usually, this implementation is I think the most important one, because it's the most energy efficient one, usually. So this is for AES, and here below I give one for Skinny. So Skinny is a lightweight cipher, and you can see the difference. First, we can implement it with a smaller area if we want. I don't say it's a good idea or not. It depends on your application, but if we want, we can implement it with actually a smaller number of logical gates. But what is more important is that the round-based implementation, so the one that is actually energy efficient, is still small. It's like roughly 2,000, a bit more than 2,000 gates, and the number of cycles then is only 40. So this is the one that is actually very interesting. This is the one that makes it actually lightweight. And that's what we want from a lightweight cipher. We want this flexibility. We want to be able to say, my cipher can fit directly my application in case I have a constraint on the area, in case I have a constraint on energy, maybe a bit of both. I need this cipher to be able to adapt easily. That's exactly what we want from a lightweight block cipher. So why is lightweight cryptography difficult? Mainly because there are many dimensions you have to consider. So I will try to go through some of them very quickly. So first, there are different platforms we are talking about. We're not talking about just hardware. By the way, in hardware, you have ASIC and you have Fpga, and this is very different things. You will go for ASIC if you have a high production, very high volume production, because it costs a lot to develop your own chip. So you need to make sure that the cost will average, and so you need to make sure that you're producing a lot of them so that it doesn't cost you too much. Otherwise, you will go for Fpga, where you can reprogram it, and the cost is the front cost is actually rather cheap. But hardware is not the only thing that might be constrained. Software also might be a constraint. If you think of microcontrollers for embedded systems, you might have microcontroller on 4 bits, on 8 bits, and that's actually very, very constraining. Most of the crypto algorithms are not designed to work with a 4-bit microcontrollers, for example. This is devices that have a very low amount of memory, and that will require a lot of cycles to actually perform your encryption, and this can be a problem. Now, even if you zoom, even if you consider that you have fixed one platform, each platform will have different options, I would say, different parameters. So for example, for ASIC, you have different technology nodes. You don't have just one type of ASIC. You have different how small you can write your transistor in your chip, basically, and also you have different libraries between the different manufacturers. So this table, for example, give you for different library, different logic process, what are the costs in terms of logical gates for the NAND, NOR gates, the NOT gates, XOR, etc. So all these gates are the kind of logical gates we use to build a crypto, one symmetric key ciphers. And you can see that the numbers can change a little bit. And if they can change a little bit, it means that one cipher that used to be good might be a little bit less good before or after changing the library. However, that being said, I have to admit that in this case for ASIC, it will not change completely. Okay, if your cipher is rather good, is rather lightweight, it's not because you're going to change the library that it's going to be becoming completely bad. Of course not. Okay, but you have some small differences, especially for XOR, for example. You can see it goes from 3 to 2, and we use a lot of XOR gates when designing ciphers. If you look at Fpga, also you have different options because you used to have 4-input lookup table technology. Now it's more 6-input lookup tables, but I think 8 is coming as well. And this might change completely if you have a cipher that manipulates a lot of 6-bit input functions. Well, then depending on the technology you'll be using, you might have a very, very fast implementation or not. Also for microcontrollers, 4 bits, 8 bits, 16 bit, 32 bit. This will change a lot depending how you are manipulating your bits in your cipher. You might get very, very different implementations. Also the memory, you might be constrained on the ROM, or you might be constrained on the RAM, or maybe both. Depending on the cipher you're using, you might have a big difference. The instruction set also is important. Some microcontroller will have already some hardware implemented special functions, and these functions might be helping a lot. For example, if you think of for example, if I can permute the bytes in some words, this will help me a lot for many ciphers actually, if I have directly this instruction. But if it's not there, it will cost me a lot. You also have different types of implementation. Like I mentioned, you can implement your cipher with just 1-bit data pass. That's how you get the smallest area, but it's going to take a lot of time to perform. And you can go then to the middle one, I would say, the round-based implementation, where you encrypt, you handle in one clock cycle and one round of the cipher. And you can go to the completely other side of the spectrum, which is fully enrolled implementations. In this case, you implement the entire cipher, all the rounds of the cipher into one clock cycle. And this is covering the case where you want very low latency. And there are some applications actually that require this. So, well, you have very also different type of implementation trade-offs. But I would say for lightweight application, what we care the most is serial implementation a little bit. If you want to target really, really extremely constrained devices in terms of area or memory, then yes, maybe serial implementation are the one that you care. But for most of application, I think what we care about are round-based implementation. I think this is the most important one because it should be low enough in terms of area so that it can fit in your application, and it's going to be energy efficient and also power efficient. And I think that's the most important thing for lightweight crypto is that you have many different goals. One goal, as I mentioned, can be the area or the memory. Okay, so it depends again on your applications, but it can be also the throughput. So I would say the area is a strong constraint in the sense that if you don't fit the constraint of the device, it's not like it's going to work a little bit or maybe a little bit good or a little bit less good. It's simply not going to work at all. It's simply you cannot fit the algorithm there. Well, you just simply cannot run the algorithm. So I think this is a very strong constraint that you have to respect. Throughput, on the other side, is maybe a softer constraint in the sense that for most applications, we not care too much, but it cannot be too bad, right? You don't want to, if you come with a smart card and if it takes 2 seconds on your subway to enter, you're not going to be, of course, happy. So for many applications, you don't care if it takes 1 millisecond or 2 milliseconds, but it should not be worse than a certain threshold. Energy consumption, this is important, especially for battery-powered devices. So if you take active Rfid tags, they're going to have a battery attached to it. They can be a bit costly if you produce a lot of them. they're going to be sent on field, and you don't want to replace them. If you have to go back on field and try to find all your RFIDs and replace the battery, etc., it's going to cost you a lot. You don't want this to happen, so you hope that their lifespan is going to be as long as possible. So energy consumption here is going to be very important. Power consumption can be also important for passive RFID tags. So passive RFID tags, they're powered from the electromagnetic waves sent by the reader, and they have only a limited power that they can use to perform the encryption. And if you cannot come up with an implementation that respects this maximum power, you simply won't be able to do any encryption at all. So this can be a strong constraint. As I mentioned, you also have latency for some, I would say, niche cases like disk encryption, or maybe also automotive industry. If you have some sensors in your car that is sent, you will encrypt the data from this sensor to the main controller unit, and well, you must be sure that that the data is coming fast enough so that the car can make proper decisions. Of course, otherwise it will have very, very bad consequences. And also, one last comment on this is that generally think of performance for lightweight crypto being a little bit different from classical crypto in the sense that usually you care for small messages. Okay, if you consider that the device is very constrained, you actually also consider that it's not going to probably be deciphering terabytes of data every day. Okay, so this is different from a high-end server where you want really a lot, you want to handle many connections, and you want to encrypt movies or whatever, then you really want something very fast. Here, it's not really the case. We only care about small messages, mostly. On top of that, you have other considerations to make the problem even more complex. What about side channels, for example? So side channel is when you can have access to some information about the device, for example, its power consumption, the electromagnetic waves coming out from the device when doing the encryption, and you can use all this information to correlate it to the secret key that is inside, and it works very well. You can break very easily devices and recover the key if the implementation is not protected. And as I mentioned, these devices are very likely to be on field in a very physically insecure environment. So I think they are even more subject to a side channel analysis than classical ones. And then in that case, what if your cipher is very lightweight when unprotected, but it's very bad when you apply side channel protection? And then in that case, well, you kind of failed because in the end, people will try to come up with to use the protected one. So maybe for some application, we don't care about your efficiency when the implementation is not protected. And one last point is the server side. So if you think of many sensors, for example, sent on field, maybe you're going to have one device, one controlling devices that's going to communicate with all these constrained devices on field, potentially millions of it. And if you don't want to overload the server too much, you need to be able to handle all this communication from all these devices in a fast way. So the server side has to be also not too bad. So the server is not constrained, but you need to make sure that there is an efficient implementation so that you can handle many connections at the same time. Usually, this is not too much a problem because there's a special type of implementation called bit-size implementation that you can usually apply on the server side. Usually, this is fine. All right, so for this talk, I need to make things a bit simpler. So I will consider that we only care about ASIC, okay? So because it's the simplest to analyze and to take a look at. So just try to remember these numbers. Basically, a gate like an AND gate, an OR gate will be one. So it's the basic unity, okay? So it's one gate, and an XOR costs you about 3 times more, okay? So that's already something that is bad for cryptographers because we use a lot of XOR gates. So it costs you 3 times more than an AND gate. And on top of this, and this is even more a problem, so the memory bit, so if you use some flip-flops to store your data in your cipher, it will cost you roughly 6 gate equivalents, which means you really can see already what lightweight cryptography designers will try to minimize. All right, let me drink a bit. All right, so how to design a cipher and how to design a lightweight block cipher now. So first, maybe many of you already know how ciphers are designed, but just in case. So how we design ciphers. So first, know that designing a very secure cipher is very easy. We know now very well how to have extremely strong arguments for many types of attacks. So we know how to design secure ciphers. We also know how to design efficient one. What is difficult is to have both security and efficiency at the same time. And now the efficiency is a little bit different from before, because now we want efficiency in terms of lightweight. So all the different criterion I was talking about before. When you design ciphers, you have two main things you want to ensure. And this dates back to Claude Shannon in 1945. So diffusion and confusion. Very briefly, diffusion means that you want the dependency on your output bits from the key bits and your ciphertext bit to be very broad. So you want very quickly to have many bits depending on many bits of the input. You want the dependency to be very large, and you want it to be very fast also when you apply your rounds of your cipher. So this is what the diffusion is about. Confusion is more about the quality of this dependency. So you want to make sure that the dependency is not a simple one, like a linear one, for example. So you want the algebraic degree, basically, if you write the algebraic formula of your entire cipher, you want the algebraic degree, for example, to be very high in many of the bits. So how do we apply these two confusion and diffusion concepts in the cipher? So let's take a look at the example of a block cipher. When we design a block cipher, we actually use an iterated block cipher. Iterated block cipher means that we take a one round function that we're going to iterate for many times, a sufficiently number of rounds so that we know it's going to be secure. We are confident it's going to be secure. Why we do that is because it's simple for everyone. It's simpler for the implementers because they only have to implement one small round function and to repeat it with a for loop, for example. Also in hardware, it's going to be better because you just have to use some multiplexer to repeat the same circuit again. It's going to be actually cheaper. And also for analysts, for crypt analysts that want to analyze, this is going to be simpler to have one function repeated many times than every round having a different function. So we use this iterated construction, and what I draw here in blue and in orange. So in orange is the round function. So that's what the function that's going to update the internal state of the cipher. And this blue part is the key schedule. So you have the key coming in your block cipher, and you're going to use this key schedule to generate some subkeys. And those subkeys are going to be incorporated inside the internal state at every round. Okay, and that's how you create your cipher. Now I'm going to zoom again more inside the F function, the orange part. And what we usually see is something like this. So it's not always the case. There are different families of ciphers, but one very large and very popular family is this one, so SPN ciphers. Basically, what you're going to have is a layer of this S here, these S boxes, and then a layer L for linear diffusion. So this S is basically providing the confusion. Okay, so this is a small S box, it's small table lookup, basically, usually 4 bits, 8 bits. In the case of AES, it's 8-bit AES S box. And this is supposed to have very specific cryptographic properties to make sure that you resist a certain set of attacks. And after that, after applying all the S boxes everywhere, you're going to have a linear layer that's going to be here to make sure that you have a lot of dependency between all the different S boxes. So this is one round. After that, you XOR the subkey and you repeat that many times. In the case of AES, for example, it's 10 rounds. And you hope that your cipher is going to be mixing everything and in a complex way enough so that you have something secure. Yeah, so this is the S box. This is the linear part. Now, this is how to make a cipher, how to make it lightweight now. So again, remember that when we look at the numbers in terms of gates, logical gates, one NAND gate costs 1, XOR gates costs 3, and a memory bit basically costs between 6 and 4, yeah, between 4 and 6. It depends on the technology that you're using and the type of flip-flop that you'll be using. But roughly, you can think of a factor 5, for example, for memory. So a natural thing that people try to do as a designer is to try to make the memory smaller. Okay, so most of the ciphers that we are using today, so AES, for example, has a 128-bit state with a 128-bit key. So the natural thing to do is to use something smaller. We reduce the block size to 64, so a smaller block size. And also the key might be reduced maybe to 80 bits, because 80 is maybe for some applications still okay in terms of security. You're not going to be able to brute force to do the 80. So it's going to be fine. And you directly get a lot of savings here. Just in terms of memory, the savings that you get are really, really huge. So the first lightweight block ciphers that were proposed, they had actually a very small block size of 64 bits, and sometimes a key size also that was very small, 80 bits. That being said, now I will not advise people to go with these sizes unless your application is so constrained that you have to use this small size, otherwise you cannot fit in your device. Then, okay, what else can you do? But if you can allow a bit more, I would advise you to use at least 128-bit blocks size. People have shown that if you use a block size that is too small, and if you start using handling a lot of data, you might have weird things happening at some point, and your security is actually reducing a lot. So yeah, try to use 128 bits if you can. Another thing that people try to do is not reducing the direct memory of the cipher, but the temporary memory. Because when you compute your cipher, when you perform the run function, you might need some temporary memory to store your variables at some point. And so, for example, one design, I was actually co-designer of this one, LED. What they try to do is to come up with a diffusion layer that has a very good quality of diffusion, but in such a way that the temporary memory that is used is very, very minimum. And so temporary memory is reduced. It means that you're going to save a lot on the implementation. Another thing that's another strategy that people try to do is to have a small key schedule. So, or maybe even non-existent key schedule. So the key schedule, remember, is the blue part in here that handles the key. And usually in most cipher, this can be quite complex because you want to make sure that the key is well mixed inside your state at every round. But well, if your security allows, and if you're sure of what you're doing, maybe you can completely get rid of this and have a very, very simple key schedule. And that's what a lot of ciphers in lightweight crypto tried. Unfortunately, sometimes with some success and sometimes with less success, because there have been a lot of lightweight block cipher that has been broken. And very often it is because of the key schedule that was sometimes a bit too weak. Again, speaking of LED, actually, so the same cipher I mentioned before, in LEDs, there's no key schedule at all. So the key that you have as input is XORed directly to the state every 4 rounds. So basically, not every round, but every 4 rounds. And so you don't even have any key schedule at all. And this has another advantage, is if your key is not modified at all, well, you can actually hardwire it. So if you have if you think of specific application where your device is sent on field and you're never going to touch it, never going to reprogram it or anything, you can actually hardwire the key directly inside as constants. And this will save you even more memory potentially. So another techniques that people have been using is to, so this actually was used by the NSA in Simon and Spec. I think the first time that from what I remember, that's seen that is from the NSA cipher Simon and Spec. The idea is that instead of having an XOR of an entire subkey coming in at every round, maybe we can XOR a bit less. So half of the state, for example, is going to be XORed with some key material every time. And it's going to save, of course, some XORs. And as we have seen, one XOR is 3 gate equivalent. So if your state is not too small, you're going to be saving a lot of gates from this trick. Of course, you need to be careful, because if you're XORing less key material every round, it means you have less mixing of the key inside your internal states, and you have to make sure you know what you're doing, and you have enough rounds to not come up, so that nobody can come up with some attacks. Also, constants. So you need constants in the ciphers because when we are designing cipher, we use a lot of structure to make it simple to analyze and to implement. And you need to break that structure. If you have too much structure, you might have some symmetries existing. And those symmetries can be really dramatic in terms of security. There have been actually attacks using this kind of issues. So you need to add constants to break those symmetries. And well, if you need constant, you need to store them, these constants. If you use all the first digits, that 100 first digits of pi as a constant, well, you need to store all these digits somewhere, and it means going to mean memory, and it's not going to be good for you, of course. So what people have tried to do is to use instead a constant that can be generated with a very, very simple and cheap lightweight function, typically a linear feedback shift register. This is very cheap, and you ensure that your constants will be different for that many rounds. So you're sure the constant will be always different, and it can be generated, not stored, but generated just using the state of this small LFSR. And this is another improvement that you can do on the saving area. But this one, this slide here is probably where most of the improvements come, and where most of the work has been focused. So you can optimize your components. So as I mentioned, you can have S boxes, for example. You can have a linear layer to do the diffusion. Well, can you change the current S boxes, the current linear layer, so that it is more lightweight? More lightweight means it uses less XOR gates, for example, less NAND gate maybe also. If you take a look at S boxes, for example, the AES S box works on 8 bits, which is already quite big. And I think you need between 150 150, 200 gates, logical gates to implement one instance of the ASS box. If you take a look at lightweight S boxes for the same size, 8 bits, you're going to probably need like 20. So you have an order of magnitude of difference here for one S box. And actually, if you consider a round-based implementation, you're going to need to implement all the S boxes in parallel. So these savings is going to be multiplied by all the S boxes that you're computing. And so it can grow actually very fast in terms of savings. Of course, you want to use maybe more lightweight S boxes, but you need to make sure that the security is still there. If you strip it to something too small and too light, you might end up with something not secure. The diffusion layer also can be improved. One way that I will talk about this after, that is used in the Cipher present, is to use a simple bit position permutation. So instead of doing diffusion, you're just moving the bits around. You're not even using any XOR or anything. You're just moving the bits around. And in ASIC, this is basically completely free. Bit wiring in ASIC is completely free. So that's the best case. But of course, the diffusion here is very, very little potentially. Another direction that has been explored is to provide very good diffusion, but trying to minimize the number of XORs. So for example, if you take a look at the AS matrix, again, you require roughly 100 XORs to compute it on some part of the state, where actually they could have used another matrix for the same quality of diffusion, the proven same quality of diffusion for much less, probably something around 20 XORs. And again, you multiply this to all the time you need to apply the linear layer to all the parts of the states, and you get a lot of savings. So just one last word on Cipher design is also, I think there has been a shift in how we design ciphers while we saw the emerging of lightweight crypto. I think also the way we design Cipher changed, because before we used to design Cipher by starting from very good components, so very good S boxes, maybe very good linear layer, and try to assemble them and try to find what is the good number of rounds such that the security is going to be good enough. And how this was done, it was done with crypt analysis, human crypt analysis. And this is very time consuming, error prone. So if you want to cryptanalyze the design, it takes months actually to perform. So because it takes a lot of time, you really start directly with good components to make sure you don't waste your time. But now I think with lightweight crypto, it changes a bit, because what people have been doing is to start from very weak components. You know that this one's gonna maybe not provide the security that you want, but maybe if you stack enough of them and if you use enough rounds, at the end you might end up with something good enough. But you cannot do human cryptanalysis with this because you have too many. The search space is going to be too huge. How many parameters you can try is going to be too huge. But at the same time as lightweight crypto emerged, you also have another thing that emerged, which is automated tools for cryptanalysis. So we saw a lot of MILP, SAT solvers, etc., that now is doing the analysis automatically. It means you can test a lot of different configuration much faster. And I think both the lightweight crypto and this new tool changed the way we design ciphers now. Also, there's an entire part that I did not discuss, which is all the operating modes. Here I only discuss about how to build the primitives, the block ciphers, or maybe the permutation as well. They're based on the same principle, but how to design this primitive. But then you have the mode, right? The operating mode. How are you going to use your block cipher, your tweakable block cipher, or whatever, to create an entire encryption or authentication algorithm? And there are a lot of work on this, and this is something I did not cover at all. So maybe a word on the present and the future of lightweight cryptography. So here I'm going to try to explain a bit, to show a bit how most of what I think are the most interesting design, important one to my perspective, and see a bit of the history, what happened. So lightweight cryptography has been a very hot topic in the past 15 years. And I think it started basically in 2007 with the proposal of the Cipher present. Actually, Gregor is one of the designers of present. And I think this is where really the community focused on this topic of lightweight crypto. So I will talk a bit about present after, but I would mention that before present, there were actually some ciphers that can be considered lightweight. So for example, Noekion, that were proposed in 2000s was already lightweight. Maybe it was not its main goal to be lightweight, but it was already lightweight. It has other issues on its own. For example, the key scheduler is maybe problematic for today's use, I would say. Yeah, the present is not the first lightweight cipher, but it's the first one that is claimed to be lightweight. So there have been a lot of research on lightweight crypto. There have been, I think, I counted, I think 1 year ago, I tried to count how many ciphers. I think I come up to a number close to 50 ciphers that have been published. That's a lot, really, really, really a lot. So I think now the field is probably mature. I'll explain why I believe the field now is mature, and now comes standardization time. So now we need to pick which cipher we want to push so that the industry can use it safely and be sure that it has been well analyzed and get the stamp from the community. Basically, ISO and even more importantly, the NIST is the driving forces here. Interestingly, also, we had the NSA that came into the game at some points in the middle with Simon and Spec, so 2 ciphers that they proposed. I will talk about it a bit after. So why I believe the field is mature now is because when you look at what you can hope to improve now for lightweight cryptography, I think it's almost non-existent anymore. We already reached more or less the optimum now. So this is a drawing for serial implementation. So serial implementation, remember, is where you try to come up with very, very small implementation. You don't care about how fast it's going to be. You only care about the area. So this is on ASIC. So this here, this axis is giving you the number of gates, and this is giving you the internal memory of the cipher. Because of course, if you're using a large block size or large key, it will not have the same impact on the size of your implementation, of course. So you have to compare with the same internal memory size. And when you look at this line here that I drew in gray, this is giving you the theoretical optimum. It means that if you have this many bits of internal memory, and you know that each of these bits will cost you maybe 5 gate equivalent anyway, well, you cannot do away with that, right? You have to store the key and you have to store the state of the cipher. There's nothing else that you can do. Now the rest, what goes in addition to that, is all your crypto, all your control logic, etc. And actually many ciphers, they are already reaching the lines. So in terms of serial implementation, you're already basically at the optimum. You cannot do much better. Even when you look at round-based implementation, I think it's the same. We cannot really do much better. This is an example with Gift. So Gift is a cipher I will quickly mention after. You have 2 versions of Gift, one 64-bit block version and one 120 block version. And this graph is giving you the breakdown of the area for this cipher. So this again is a round-based implementation, not serial, round-based. So here we're not trying to minimize the area at all. We're trying to minimize like the area times the throughput. And when you look at the breakdown, the red part is the key. So the key register that needs to be there. The yellow part is the state register that needs to be there. And the rest now is the crypto part. So the green is the S box. The purple here is the XOR gates for some part of the design. And then the light blue is the control logic, basically. So it means that all the stuff which is in red and in yellow, in orange, cannot be removed. It has to be there. And only the rest you can potentially try to improve. So you can see that the freedom that you have to make things better is now very, very thin. And there's not much more that you can do. So that's why I think now most of the ciphers are already, in terms of performances, they're basically reaching the close to the optimum. So let's take a look at very quickly how oh, yeah, sure.
Why is the key register 2 gate equivalents smaller than the state register? It's a stupid question, but
yeah.
Forgive.
So in this one,
no, in the 128.
So in this one, why they are the same size?
No, they are not the same.
Oh, 2 gates or 2 gates. Oh, this I don't know. This I don't know. This might be an artifact of how the measurement is done about what gates belong to what.
Okay.
That's a good question. I don't know. Okay. So I just want to give you now a very brief, I'm not going to go into detail, just a very brief overview of the main designs. I think the most important one and what are the basic principle. So the first one, as I mentioned, was present. So Gregor was one of the co-authors, and I think it's a really excellent design because it's stripped down to the minimum. So they really try to come up with with something extremely simple and I think quite elegant. So that when you look at the cipher, it's again a layer of S boxes, but the S boxes are now 4 bits, so there's much more smaller S boxes. Why they do that is because, well, you can have very decent S boxes on 4 bit, which are very, very efficient. You need a very, very few operations to actually implement them. And what I think is really great is the linear layer does not use any diffusion at all. It's just bit wiring. So you're just moving the bits around. This is completely free on ASIC. So only the S box, basically, you have to pay for it. And somehow the diffusion comes from how you wire all these links here. And also the diffusion will come from the S box naturally, okay? Because the diffusion inside the S box will help you to provide the diffusion for the entire cipher. And so this cipher actually was selected as an ISO standard in 2012, so that the industry can start using it potentially. I think some industry players are probably using already present. Another one is photon and LED. So photon is a hash function, LED is a block ciphers. So this was published 4 years after present. The idea here is not to go for round-based implementation, but really serial implementation. The goal of these two primitives was to try to break record for the smallest implementation possible, basically. Don't care about round-based. And as I mentioned already, the idea of LED, and this is the same for photon, was to minimize the temporary memory. So the diffusion layer that is used in LED and photon is a very good diffusion layer in terms of cryptographic properties, but the memory that you need to actually compute it is stripped down to the minimum. Actually, there are a few NIST lightweight candidates that were based on photon, and there is one finalist. So for the competition ongoing now, there's one finalist based on photon. And photon was selected also as ISO standard for hash function this time in 2016. 2 years after came Simon and Spec. So Simon and Spec have been designed by the NSA. It was published on ePrint, so it's not a peer review in 2013. And actually the documents of presenting those ciphers were circulating a bit around some people before this date. And the first idea of NSA was to say, okay, it's going to be hard to have something that is good in hardware for constrained hardware and something that is good also for constrained software. So let's break down into 2 different designs. Simon is the design for hardware, and Spec is the design for software. And let's try to make the best we can for these 2 cases. To be honest, when I saw the 2 designs, I was very impressed because it's a extremely simple and efficient ciphers. It broke a lot of records for many parameters, for many measurements, actually. This is the Simon round function. This is the Spec round function. You can see Simon is just using some rotation here. In ASIC, it's completely free. Okay, so some rotation. You have AND gates here, and you have a few XORs. Okay, and this is it. They just repeat this very, very, very simple function to the number front, and that's it. It's very simple to implement, and the performance measures are really, really, really excellent. For Spec, they leverage the fact that on most microcontrollers you will have some modular addition instruction present. So you can use that because it provides a lot of nonlinearity for cheap costs. Okay, for just 1 cycle, you'll be able to do the addition and get a lot of nonlinearity out of it. And the rest is, again, some rotation. So Spec is very efficient in microcontroller, and Simon very efficient in hardware. The big problem with Simon and Spec is that there was no security analysis provided. They just proposed the design, and that's it. And usually you cannot do that. You have to make your own analysis and show why you selected this component, why you selected this rotation value, etc. But of course, it's the NSA. They cannot tell you how good they are at doing differential cryptanalysis or symmetric cryptanalysis whatsoever, whatever it is. They will never tell you. So they just cannot do any cryptanalysis at all. And that was a big problem for the community, even though those 2 ciphers get a lot of attention, a lot of third-party analysis, and so far no one broke it, even though the security margin for some of their version is now very thin, I think, but nobody managed to break it. So they tried to push it at ISO, but it failed. There was a big backlash from the crypto community against this, because also it was at the same, just after the revelation that there was some potentially backdoored pseudo-random number generator from the NSA in some other ISO or NIST instances. So yeah, basically they didn't make it through. One other one I would like to talk about is Skinny. That's I'm actually one of the co-designer of Skinny, and Gregor is also a co-designer. We proposed it at Crypto 2016, and the idea is that since Simon broke a lot of record for hardware performances, we wanted to have some academic one, so an academic version, trying to be as good in terms of performances as Simon, maybe even better. I think this is something we actually achieved, but with providing a lot of security guarantees and maybe a better security margin. And on top of that, provide this tweak capability that I was mentioning, so this tweakable block cipher. And this allows you to then use this primitive into much better modes that are going to have a higher security level, easier proofs, etc., and actually better efficiency. So I think here we didn't. I don't think for Skinny we provided some breakthrough. We just stay on a well-known track, but we try to really optimize all the components to really that were known, I think, at that time of the publication, so that we really get the best snapshot at this moment. I think I wouldn't claim that there's a breakthrough in terms of design for Skinny. So actually, yeah, Skinny is also, there were a few candidates from the NIST competition that were based on Skinny, and there is one finalist still on board for the competition. And Skinny is also undergoing now ISO standardization. It's in the final stage for, yeah, I don't know the names for ISO process, but it's one of the very, very final stage, and it should be a standard very soon. One last one I would like to talk about is Gifts. I'm also a co-designer of Gifts. So Gifts is basically the idea when we design Gift is we take a look at Presence. So again, I think Presence is a very good design, but it has one weakness, which is the linear cryptanalysis. So for some reason, linear cryptanalysis is performing quite well compared to other attacks on Presence. And actually now the security margin that you have on Presence is quite small. So we wanted to revisit Presence and maybe to see if we can use different S boxes than the one they use, and different bit wiring than the one they're using. So that's resistance against linear cryptanalysis is improved. So we managed to do that. And we also actually managed to do that with a cheaper S box. So we managed to have a scheme that is cheaper than Presence and also more resistant to classical attacks. There are actually several candidates that of the NIST competition that are also based on Gift, and we have also one finalist of the competition based on Gift. Okay, so let's take a look at now the competitions. So the competitions that are being organized, they did not request for encryption or authentication only. They are requested for authenticated encryption. So they are asked for a primitive that do both at the same time, confidentiality and authentication at the same time. Why they ask for this is because there have been a lot of issues by some engineers using some encryption primitive, some authentication primitive, combining them, and depending on the way you combine them, it can have catastrophic outcome. So in order to avoid this potential responsibility on the engineers, what I think people want is authenticated encryption, something that does both at the same time, and you don't have to care about misusing it, basically. So that's what they call for. And the first competition that we saw is the CASA competition. So CASA competition was a competition organized by the community, so the crypto community. Some people in the community judged that it was a good time to ask for new schemes for authenticated encryption, and to also give some dynamics to the field, basically, and to make people work on this. So this competition lasts for 5 years. It was not initially designed for 5 years, but it had a lot of I think issues with the schedule. So from 2014 to 2019, we had 57 submissions from all over the world. Many countries were represented. Basically, all the best cryptographers in the world, I think, submitted one design at some point. And you had several rounds to prompt the candidates. So if your scheme is broken at some point, someone comes up with an attack, of course, for the next round, you're not going to be selected, very likely. And also, maybe if your performance is not good enough compared to others, you might not be selected to the next round. Or if maybe you don't have enough analysis, if nobody analyzes your design, then maybe we cannot trust it so much. Unfortunately, it doesn't mean that your design is bad, but that's the kind of the unwritten rule. If you don't get enough attention, you might get kicked out as well. So after many rounds, many cryptanalysis conducted, many skins getting broken, performance measure, etc., they came up with 3 portfolios. So one portfolio for lightweight applications. So this is why it's interesting us today. One portfolio for high performance applications. So basically high speed internet encryption, if you want. And one portfolio for defense in depth, which is what if you start misusing your cipher? What can you get? So for the one that is interesting us, a lightweight application, the winners were Ascon as first winner, and second one was Acon. So let's take a look at what is Ascon then. So Ascon was designed specifically for the CASA competition. It's based on the sponge operating mode, so it's not a block cipher, tweakable cipher, or something like this, but it's more like a stream cipher kind of oriented design, so sponge. And for that, they need to define a permutation. So how is the permutation built? I think it's a very, very clean and very nice design also. So it has 5 words of 64 bits. So you can see these words x0 to x4 here. And what they do is they apply one 5-bit S-box, very, very lightweight, the S-box circuit is given here. It's a very, very lightweight S-box that is applied on every slice of the word. So you take the first bit of every word and you apply the 5-bit S-box. Then you take the second bit and you apply the S-box, etc., until you've done all the 64 bits of the words. Once you've done this is the S-box. Then the linear layer is just you take the 64-bit words and you apply these linear functions here. So for example, x0 is transformed into x0, XOR with x0 rotated by 19 bits to the right, and then x0 rotated by 28 bits to the right. And this is very nice because if you use some microcontrollers that have that are manipulating that is working, for example, on 64 bits, well, you're going to be implementing this very, very quickly. And in hardware, it's a little bit costly because you have quite a few XOR, but it's not too costly. It's quite acceptable. So I think it's in the end, it's an all-round design that is quite efficient in many scenarios. And so there were also several designs based on Ascon that has been submitted to the NIST competition, and we still have 2 finalists from Ascon currently. So maybe the most important one is the current NIST competition that is ongoing right now. So it started in March 2019. The final decision is, I think, expected for summer. I think they announced it for summer 2022, but there is COVID and maybe there might be some delays, so maybe it's going to come up at the end of 2022. I mean, I'm not the NIST, so I have no idea, but we can expect it hopefully by this year. Strangely, there was 57 submissions, so the same number as CASA. I don't know why. The submission were different. They're completely different, of course, but for some reason it's the same number. So again, same rules. You have several rounds to print the candidates. If you're broken, you don't go to the next round of very likely. And we are currently in the last round of the competition. How is the winner selected? First is that you must perform better than AS-GCM. So AS is the worldwide block cipher standard, and GCM is the mode, also the standard mode if you want to use AES to provide authenticated encryption. So this is the person you have to beat, basically. So you have to make it better. You have to perform better than AS-GCM, at least on some scenarios. So maybe you can be better in hardware, maybe you can be better in software, but you have to beat it. If you don't, then there's no point in lightweight crypto. You can simply use the current standard that we have. Hashing capability was something requested by NIST, but as an optional thing. So if you want, you can provide a hash function using the same primitive that you are designed for your authenticated encryption. Side channel, they also mentioned that it is an important criterion. It's not a definite criterion, but it is something they will take a look at, which I think is good. And also an unwritten, this is not an unwritten rule, actually, they mentioned this. The well-analyzed and well-established, whatever that means, candidates will be favored. Okay, so this is natural because they take a lot of risk when they're going to come up with this standard and trying to push this to industry. You need to make sure that there's no flaw in it. And if you don't want to have any flaw in it, you must have a lot of humans taking a look at your design. So there's a huge advantage to schemes designs that have been there for a long time, that I've seen a lot of papers published, basically, which show that a lot of people take a look at it and try to break it. Of course, you have to stay unbroken, otherwise it makes no sense. Also, I think this is one question I still don't know. I think maybe NIST is still asking themselves about it. Should they go for one candidate that does everything? This is a good idea if you think that standardization, how standards will penetrate the industry products is difficult. In that case, you might want to go for one candidate because it's not very interesting if you propose a standard and nobody's using it. So having just one single standard will increase your chances of seeing it used everywhere. But at the same time, if you have one standard and it does not fit the various scenario that you want to solve, it's not good also. So I don't know, one natural thing to do is maybe to have one candidate for hardware, one candidate for software, just like the NSA did for some spec. I have no idea what the NIST is deciding. We'll see very soon. All right, so this is my last slide. So these are the 10 finalists that we have for the NIST competition. So this table is completely biased. I am one of the designers of some candidates. I'm co-designer of Gift, co-designer of Photon Beetle, and co-designer of Romulus. So I'm completely biased, but well, I'm going to explain to you why I did this kind of a breakdown. So the 10 finalists are Ascon, Elephant, Gift COFB, Grain, ISAP, Photon Beetle, Romulus, Sparkle, Tiny Jambu, and Zodiac. You see a lot of diversity in the names. The second column gives you the type of scheme. So as I mentioned to you, you have like the permutation, stream cipher kind of based designs. So this is called like perm for permutation. You see that you have one block cipher based here with Gift, one stream cipher based with Grain, and one tweakable block cipher based, which is Romulus. Some of the design, actually, I put them in permutation, but they are a little bit in between permutation and some other things. So well, it's not, everything is not black and white here. So the third column gives you the internal primitive. So what kind of primitive are you using inside? So here you can see Ascon permutation is used twice. So it's used in Ascon, but there's another one, ISAP, that is used as well, that uses as well Ascon. And why I put some in green and one I put in red and one in white. The green one is, I think, the well-established one. So these designs have been there before the competition. They were proposed before the competition, and they received quite a lot of attention. There have been quite a lot of papers studying it. And yeah, I think we can really trust their security at this point. The red one, I don't say that they are not secure. So far, there's no attack whatsoever, but they have been created, the primitive inside those two candidates have been created just for the competition. And I think somehow they attracted less analysis. Again, I don't mean at all that they are bad design. They are still completely secure, and I do believe they are very good design. Xudu is a little bit in between because it was published just before the competition. So it was there before, but maybe not as much analysis, I think, as at the other ones. So that's why I put it in white. The next column is a security margin. So all these internal primitive might be broken or unbroken. By broken, I only mean the internal primitive. Maybe this has no impact at all on your overall design. So for example, for Ascon, the Ascon permutation that is used inside the design, you can find distinguisher quite easily for it. But it does not mean because you can find distinguisher that you can actually break the design, not at all, okay? But some design, they do have internal primitive that still have the full security. But what I mean is that, for example, if you take Gift or Skinny, so far there's no known a distinguisher known even for the internal primitive. So even if you could break the internal primitive, does not mean you can break the entire design, but even the internal primitive is still not broken at the moment. The next column is the claims. So the claims, so you have different security claims depending on how much data you allow the adversary to get, and some of them will be proposing birthday bound, which means in a sense 2 to the 64 basically data. So up to 64 you're guaranteed to have security, but after that there's no more guarantee at all. Does not necessarily mean that it's going to be broken, but at least there's no guarantee anymore. And for the one in green, it means that even if you use more data than this, there is still a guarantee of security. Then performances for hardware, for software. So the green one, of course, this is again very biased, and it's hard to put in groups. This is so complex to compare hardware and software, but I try to try to put them into buckets anyway. So ISAP is having bad performances, but ISAP is very special because ISAP is having a sidechain resistance. So this is a very strong security guarantee that you're providing, and it takes a lot of computation to do that. So this is natural. I think that ISAP has a bad performances, but it kind of lives in a different world. For the rest, well, that's my personal view on what is good for, I mean, what are the performance for advanced software. And yeah, some of them have hash capability, some of them do not have. So my personal take, I'm not the NIST, and maybe some people will not be happy with what I will say, but that's my personal view on the competition. I think some of my design will not win at all. For example, Photon, I think is unfortunately not having performance that is good enough to make it win. Photon is very good for very small area implementation, but for round-based, I think it's not good enough. So I think, for example, Photon will not make it. I think the Elephant has the same problem as Photon, so I think also Elephant, my personal view, will not make it. ISAP is a bit special also. So ISAP is very linked to ASCON. So probably if ASCON is selected, maybe ISAP will be selected at the same time. I don't know, but I wouldn't see NIST selecting ISAP alone because it's a very special use case here. My personal view is Sparkle and Tiny Jumbo will suffer from the ad hoc thing, the fact that there's not been as much analysis on these two designs as the rest, even though they are very good design, very good, excellent performance. But I think this might be, maybe the NIST not choose them. So my personal view is that the rest is ASCON, GIFT, ROMULUS, and Zodiac are, I think, as the main candidates, and the one I expect to see, one of them I expect to see winning. Well, let's see if I'm wrong or not. So that's it. That was my overview for the lightweight crypto. So again, I'm sorry, I was a bit too long, and I didn't cover everything. But if you're more interested in the originally, I plan to talk more about Romulus, one of my candidates. But I prefer today to just give an overview. And if you're interested in Romulus, you can take a look at my website. I have some presentations there, and when I give I present Romulus to you. Thank you for your attention.